So, according to the plan, today's lecture is about modeling structure. I put these two side by side because I could just as well start with modeling behavior. The process is a bit hazy on this. So once you've done your use cases and your requirements engineering and all that, you can either go by doing modeling some structure, doing a domain model, a conceptual map of your understanding of the problem domain, or you can jump right in and start modeling the behavior of the system. In the end, you're going to do both anyway. It's just a matter of what you start with. The benefit of doing the structure first, the conceptual map, is that you have something to attach your behavior model to, especially since we want to mimic reality as much as we can. So when we see that the real world problem domain consists of certain concepts and attributes and relations between those concepts, we would expect our software system to have software entities, objects, and so on, that more or less tries to mimic what we see in the real world. And if we haven't done an attempt to at least map out the real world first, we will have a harder time to understand what we should mimic, really. So while I do put these two side by side, it makes sense to start with modeling structure, but it's not something that you're going to do all of the structure modeling first and then all of the behavior modeling then. You are going to work hand in hand. You're going to do a bit of structure modeling, you're going to go over and do a bit of behavioral modeling, and based on what you learn there, you're going to update your structural models and so back and forth and so on. Modeling structure. First thing is, as I mentioned, then a domain model, or conceptual model it's also called. The idea there is that we want to see what entities are available, what concepts are working together in the problem domain. We want to find our concepts. We want to find attributes to those concepts. We want to find their associations. And we'll get to the difference between an attribute and a concept, but the general idea is that a concept is something sort of tangible in the problem domain. It's something which is slightly bigger. It's something which plays an importance, that you think that this concept has a certain significance. Whereas attributes are obviously then just values or sub-values to each concept. We'll get slightly more to that later. We can start, as with any activity really, we can start with a checklist. This is not a complete checklist, it's just a list of categories. You can probably find other categories in the systems that you build. The idea is that by having a list of categories to begin with, you have a starting point. You have something that you can at least start looking in these areas. If you, at the end of the day, look through your categories and you realize that you don't have any concepts in one of the categories, that might be a warning that either you should look further there, or that it's simply this category is not relevant for this type of system. If you don't have transactions in the system, for example, well, then sure, that category will be empty. But if you're not sure and you realize that the transactions category is empty, and well, it's a good idea to look further there. Maybe you do have transactions, but you forgot about them. You didn't look close enough there. So that's how you work with these checklists. It's not that you have to have items or concepts in every category. It's suggestions that do look here. If you haven't looked already, do look here. And as I said, you can always add more categories as well. Physical objects in the problem domain, that's the first category. That's the one which is obvious that we want to have. If there is a physical object in the real world in the problem domain, we want to mimic that in our software system, probably. So in the course book, the point of sale system, the actual point of sale terminal is a physical object. If we take another domain, an airplane or airport, then the aeroplane is a physical object that we can model. Places, so the store is a place, an airport is a place. Transactions, so anything that records a transaction. It's not well, records are a category in their own, but if we want to have some sort of representation of a transaction, we have paid for whatever we bought at the store, for example. We have reserved a seat at a flight. We have, of course, paid for the flight as well. We might have other transactions there that we get this boarding pass where we say that we get information about what seat we have on the plane and so on. That's also in some sense a transaction. The actual boarding pass. The actual boarding pass is a physical object. It's also a transaction. So you also see there that the categories is in no way that you have to be in only one category. You can be in many. The same concept can be many categories, and that doesn't really matter as long as you find it. That's the whole point of doing this exercise. Containers, things that contain other items, a shopping basket, an aeroplane, a folder with tickets in, whatever. And then the things in the container, the items that I want to buy, a liter of milk, a kilo of bananas or whatever, a passenger in an airplane, the seats in an airplane, are things in the container. Events, things that happen in the system. We make a sale, we purchase an item, a flight arrives at the airport, or a flight leaves the airport. Those are events, and might be interesting and relevant to model in our system. Descriptions of things, we keep those separate from the things themselves, simply because that's usually how it works in the real world. You don't have, if you pick up a liter of milk in the supermarket, it's the liter of milk. It's not the physical qualities of milk or where the cow grew up or anything like that. If you're interested in that, that's a separate thing, the description of that 1 liter of milk that you bought. That one, the description of a thing has information that might be useful. For example, if you're in the supermarket, the price of the milk and so on, the barcode of the milk, all of those things are part of the description, which means that you can have one description that fits all the liters of milk that is in the supermarket. You can have many items related to the same description. The description of a flight, where it leaves, where it lands, speed, distance, and so on. Those are descriptions of a flight. How many passengers it's got booked, who flew, who's the pilot, who is the ground crew, and so on. And things that record our transactions and keep some sort of transient record of it. Or permanent record, could be transient as well, but permanent record in particular. So if we have a receipt of our sale, if we have some sort of, the ticket is a storage of storing the information that we have flown somewhere. A passenger list on an airplane, that's a record of a flight. Contracts that we've entered, that I have now booked my flights, but I haven't paid for it yet. I will pay before a certain date. That's a contract of a transaction that is going to happen at some event. Usually, in this case, it's a date. So with these categories, we can start building an understanding of how does this problem domain work. And it's not about what we are going to build. It's not about how we're going to build it. It's just a matter of mapping out, this is the reality as we understand it. Then we can start deciding on what is relevant for us to build, what part should we build, how should we build it, should we even use an object-oriented programming language for it, what should we do? That's the next step. This is something that you can start doing really in any course you're taking as well. You do mind maps, for example, on a course. You can map out the domain concepts and how they work together as a study technique if you want to. This is also not something that we do once and we're done with it. We do it continuously. We start with something. This is our current understanding of the problem domain. But as we do more use cases, for example, we learn more about the problem domain. We talk to the customers, we find new stakeholder groups, and we interview them. And as we learn more, we will add and extend this domain model. One thing that most concepts have in common is that they are nouns. So when you look at the descriptions that you have, you can look in your requirement specification, you can look at your use cases, you can look at any other textual description of the problem domain, you can look at competitor products, you can look at bug databases and legal documents describing the domain and whatever. When you are looking at these documents, these texts, you will be keeping an eye out for nouns, things really. And these are likely candidates to be concepts. Some of these concepts might be attributes, but again, you're building an understanding. It doesn't have to be perfect in the beginning. So some things you will decide already from the beginning that this is an attribute. I'll put it into the correct concept. Or you might guess that this is a concept, and then later on you realize that, nah, it wasn't that important. I can do it as an attribute instead. So you don't have to be finished or carve things in stone from the beginning. You learn as you go. And you should also be aware that natural language is ambiguous. You know this, of course, but that means that you can't just say every noun is a concept. Sometimes they're not, and sometimes you only see the verb form of a noun, and you have to sort of deduce that there is probably a noun somewhere behind this verb form. But it's a good rule of thumb, at least, that looking for nouns is a good starting point, at least. Attributes, they are more the logical values of a concept. So you can have, for example, you can have a concept which has a name, it's got a quantity, it's got a status, whether it's available or not, for example. A tip there is to look for things that you can represent with built-in data types. If it's a string or an integer or a date or something like that, then if it is only one of those, a string, int, or a data, so then maybe, likely, it is just an attribute. Sometimes slightly more complex things like an address where you have several text fields, or a person number, social security number, or things like that, could also be a built-in or could be an attribute, even though you have to actually represent it as a class in its own right. But they are still relatively simple entities. But it's not always the case. Sometimes something that you think is as simple as a string could be important enough to be represented as a concept anyway. So the flight number, for example, or the flight, maybe you see the flight as just a string consisting of departure gate, arrival gate, and time, and the flight number. That's a simple string, right? So you don't need to have a concept for that. But the flight in itself is probably an important thing of how you run an airport. So it's easy to pass around an object and say that this is a flight, even though that flight might just contain that one string. It's still easier and closer to how the problem domain works if you treat that as a concept. So the moment you realize that something is more complex and has an importance of its own rather than just as a value on some other concept, then it probably is a concept. But if you can keep the attributes simple, something that is really just attached to another concept and doesn't really have an importance of their own, then that's a good rule of thumb as well. That keep them simple, keep the attributes simple. And as I say, you can always change. You can always convert an attribute into a concept or vice versa as you learn more. Note also then that even though we try to mimic the real world when we build our software system, this is one of the areas where we will probably make a few changes. We will realize as we start designing the system closer and as we start building the system that, yeah, not all concepts did end up as concepts in the code. Some of them did end up as attributes and vice versa. Some attributes looked simple but were actually not a simple built-in data type, so we needed a class for it. So we'll create a class to represent, for example, an address or a phone number. A phone number has verification built into it, and it's got area codes and so on. So we'll probably want the class to do phone number verification for us. Even though in the problem domain it's just an attribute of of a person, for example, that they have a phone number. So sometimes the mapping between the conceptual model and the code that you actually build in the end isn't as clear. It's not a one-to-one mapping. You will transform some of the attributes into classes, and you may transform some of the concepts into attributes on classes. Associations. So as we have a number of concepts, and of course they are not standalone entities. They will of course collaborate in some way in the problem domain to do whatever, to work in the way that whatever the problem domain works like. So what we do, we want to model these associations between the concepts. So it's a relationship between concepts. It's a meaningful relation. It's an interesting connection. It's not just that, these look like they sort of belong together or whatever. It's actually, you see that they are doing something together. A flight has passengers, for example. All right, that's an association. But the passengers may talk to each other during the flight. Well, is that really relevant for the problem domain? Probably not. That's a side effect of them being squeezed into the same flight together. It's not something that has to do with the problem domain as such. There are, of course, several types, more than these types, but one type is that we, for some reason, need to know about this association. It could be for some time. For example, that the flight and the passenger, they are related for the duration of the flight at least. We want to know if something happens with the flight, for example, what are the names of the passengers and who are their next of kin and whatever, or just the fact that we want to figure out who ordered what meal. Did anyone order the vegetarian meal or whatever? So we want to have that association during the flight. Who is on this flight? Where are they sitting? Did everyone arrive to the flight and so on? After the flight, we probably don't need to maintain it for as well, but it's still a record of who flew, so maybe we'll keep it anyway. Those are the things that will probably have a representation in our software system, these type of need-to-know relations. Some associations will just add to explain how the problem domain works. They might not actually make it into the software system. So it's just to clarify the problem domain. And that's okay as well. Again, not everything has to be turned into the software. It's the meaningful parts that we turn into software. The associations, again, checklists, and with everything that I said before about checklists. But if one concept is a part of another concept, so if I'm doing my point of sale system again, the sale item, each item that I sell, the liter of milk, the bananas or whatever, is part of one specific sale. The wings are part of the aeroplane, the seats are part of an aeroplane, which is probably a better relationship unless I'm doing aeroplane maintenance. One item or one concept is contained within another concept. So the items in the store are contained in one particular store. That's useful if I'm restocking the storage, for example, so that I make sure that I order new milk as I sell out the old milk. One seat is associated with one flight, is contained within a flight. Probably only one flight at a time, so I don't oversell one seat. One concept is a description for another concept. Here's again the description category of concept. So the item description is associated with the item itself. The flight information is associated with the flight itself. If one concept is known or is recorded in another concept, so one particular sale is known to the point of sale system, and it's recorded there so that I can go back and see that this sale has happened. We are down 1 liter of milk in our stock, and we're up whatever the price of a liter of milk is in our cash box. A booking is known to a flight, so that they when the flight is planned, they know how many bookings have been made to that flight, and so on. And one concept can fully own another concept. This can be in the business sense that a store is owned by a company, but it can also be in the more abstract sense, or perhaps even more concrete sense, that, for example, the wing is owned by the aeroplane. I put that up in another category, but again, categories, one relation can be part of many categories. The point is to find them, not to classify them as such. Related transactions. So the sale is one transaction in one sense, that you have this milk and you have the bananas and whatever, that's one transaction really. And then you can have the several other transactions related to that where I do the payment, and I can do payments, for example, in installations. I can do payments by working off my debt, for example, so I can do different types of payments to the same sale. So those payment transactions, they are related to one concept, one sale. A booking is related to the tickets, because once I've made a booking, then eventually once I've paid, which is another related transaction, then I will get a ticket, and those two are related, that the booking and the ticket map to each other. So multiplicity, let's see if I have, there we go. Multiplicity is simply how many of the objects on either side are available. So if I have two classes, if I don't say anything, I'll just put a relation between them. That's one level of multiplicity where I don't say anything. So I have no way of knowing now how many A's and how many B's I have. So if I then qualify this, and I say, for example, let's put a number there, a concrete number, and let's make this into the other direction because it's easy to read then. So the way I'm supposed to read this is that if I have one object of the type A, it will be associated with exactly 5 objects of the type B. I still haven't said anything about the relationship between B and A, so it's undefined, and I'll come back to that. But what I've said now is that for every A, there's exactly 5 B's associated. So if I want a range there instead, I can do that. And now what I'm saying is that for every object of type A, it's associated with at least 2 objects of type B and at most 5 objects of type B. I can put association or put multiplicity on the other side as well. Let's say 3 there. And now what I'm saying is that the way I'm reading this is that if I have one object on this side, I have so many objects on that side, which means that now I read it on the back on the other direction and saying that if I have one object of type B, it will have exactly 3 objects of type A associated to it. So these are hard-coded cases, if you like. More commonly is that I see some form of wildcard signs here. Your usual regular expressions work. So I can put an asterisk there, and that means that I have arbitrarily many. I might have, if I have an object of type A, it might not have any current associations with any objects of type B, or it might have 100, 1,000, or I don't know. So this gives me an indication of what data structure I should pick when I implement this. It's not explicitly specified in these relations, but typically if I only have an association on one side, what it would mean is that I'm probably going to read this that A is somehow the originator of the relations because the asterisk is on that side. If you've studied database design, you would probably implement it the other way around, but in object-oriented programming, when you do pointers and so on, this is probably, you would probably read it as that objects of type A has a collection of objects of type B. I can say one or more with the plus sign. Same thing there. Now I'm saying that there is at least one object of type B associated to each object of type A, but it can be arbitrarily many. I can also, often you would see, to be really clear, you would see a 1 plus, meaning that you basically just make very clear that there is at least one, and then arbitrarily many. If I want to say that the same thing with an asterisk instead of the plus sign, I can do that just as well. I can say that I have at least one and up to arbitrarily many. What else I can probably, of course, I can also say that I have a certain number and more. In the same way, I can say this. What this means is that I have at least 5 and as many as is needed. So if we do a concrete example of this, flight and seat, I can obviously say then that flight is associated with seat, and it has, well, if it's a small airplane, maybe I'll just hard code that. If all airplanes only have 10 seats, I can hard code that. And if I have bigger airplanes, I probably don't want to keep track of how many seats can be available in any airplane, because the size may vary quite big, quite substantially from one airplane to another. So I'll just put an asterisk. And I might also say that the same seat can be sold on several flights. If I have, for example, collaborating airline companies, each company has their own flight number, and the same seat might be sold to a passenger, but with different code, different flight numbers. So I could actually have one seat part of several flights as well. Probably at least one. Because if a seat isn't associated to any flight, then it's just flying around without making money. So at least one flight, but could be more, and arbitrarily many seats. Note here now that I am expressing a static relationship. So this is the static modeling, the structural modeling. That flight is associated, all flights are associated with all seats in some way, and these multiplicities say something about that. But these multiplicities say things about a running system and the restrictions that I put on a running system. So I'm inside of my structural modeling, I am giving hints to my dynamic modeling of what can go on here, how many can I have in a running system. So when I read these associations, I read them with as if I had objects. So if I have one object of the type flight, it's associated with arbitrarily many objects of the type seat. And one object of the type seat is associated with one or more objects of the type flight. What else is there to say about these? Oh yeah, if I don't write anything, if I just do let's add another flight, or maybe two other objects. If I can do it like that, I probably should be able to. Yep. So if you don't see any multiplicity, which is not uncommon, especially if you're doing the domain modeling, you don't have that much information yet, so you will wait with adding these multiplicity tags until you actually know something. If you're a UML modeling computer scientist, then you will say that if there's nothing written there, it means exactly one. So it should be read here that for every C there is exactly one D, and for every object of type D there is exactly one object of type C associated with it. To me, a more pragmatic approach is to say that if there is nothing written, it means that I haven't specified it yet. It can be one. It probably is one, but it doesn't have to be because I haven't specified it yet. So more information is needed, really. As I say, in the domain model, it's not uncommon that you don't see these multiplicities because you don't have that information yet. But you can also see, if you see something that this relationship, it's obvious that it's going to have this special multiplicity, then you might as well add that. Anything you learn, you might as well put into your models, because that means that you've coded that information so others can read it. As you transform your domain model into a class diagram, you will probably add a bit more of these multiplicities, but even so, there might be, or there will probably be relations that you don't put any multiplicity on because, well, it's obvious, or you haven't studied it yet. It'll become obvious once you start coding it. But you will probably see more of these associate or these multiplicities as you transform into a class diagram. The domain models is so we reuse the same syntax as we do for the class diagram. So this is, as you see, this is a class diagram model or class diagram. We have empty places for attributes and relation and methods. And the only thing that says that this is a domain model and not a class diagram is that, well, I say so. You can't really look at the diagram and say, is this a domain model or is it a class diagram? It's a matter of when is it being used. What is going to happen as you continue working with this system is that you will do dynamic modeling of and behavioral modeling of some of the parts of the system, and you will borrow concepts from your conceptual model and you will upgrade them into classes. So eventually you'll fill in more details into the classes or into the concepts, which will then be intended to be used as classes. So eventually you come to a point where you will have something which you think, well, I could build a system. This is a blueprint with enough detail so I can start coding this. And then you have a class diagram. If you don't have that information, if it's a bit vague, it's not down that many methods in it, the attributes are a bit sketchy and so on, relationships between objects are, well, not clearly specified what type of relationships they should be and so on, well, then it's probably a domain model. So you can use that to understand the problem domain. You can use that to see how the problem domain works and what you might want to build classes out of, but you don't have enough information so that you can actually build the classes. And then it's a domain model. As you fill in more information, you slowly transform that into something which is closer to a class diagram. Which is basically the next slide then. One more before the break. Aggregation. Aggregation is something that if I want to express a closer relationship between two objects, or concepts, if I have two concepts that are, well, normally associated, that's usually enough, and especially if I do the domain modeling, I just use association. As I start doing a class diagram out of it, I might want to express that some objects or some concepts or some classes are more closely related to each other. One class might have a stronger ownership of the other class in some sense. Then I can start using aggregation. There are two types of aggregation. There's aggregation and composition. I am a bit sketchy of which is which, whether you should use the hollow diamond or the black diamond to model these. But the long and the short of it is that if I want to express something which is a slightly clearer ownership, I will use aggregation. The way to read them is, in these cases, that the team aggregates persons. So the team is the owner in this case of this relationship. The diamond is on the owner side of the relationship. And so what we're saying with this top one is that a team consists of one or several persons. And each person can be associated with 0 or more teams. The bottom one, a car consists of 4 wheels. Of course, it consists of other things as well, but at least 4 wheels. And each wheel is associated to one and only one car. This type of relationship is perhaps more important to model if you are using a programming language such as C++. where you can make a difference between having a pointer to another object and having the object itself, or enclosing that object inside another class. In programming languages such as Java, it doesn't really matter because everything is a pointer, so everything is an association. So all that this adds is a bit more information about who should manage that relationship, if that wasn't clear before. What I've seen with students on exams and so on is that there is a tendency to want to use aggregation at least once on an exam to show that you know it. And that means that you almost always get it wrong. So my advice to you is to, unless you're really, really certain that you are doing it right, don't use it. These things can just as well be modeled with an association, and you won't be wrong with an association, but you might be wrong with an aggregation. So avoid using it unless you're actually certain that this is the right thing to do. But if you see it in a class diagram that someone shows you, then you can read it as say that there is a stronger relationship here. It's just a loose association. There is an owner side and an ownee side, if you will. Okay, so I suggest we take a break there and reconvene at a 1/4 past. And then we'll continue from there. Right, here's a brief example I cobbled together in all of 5 minutes before, well, a few years back. The first discussion we could have here is this a domain model or is it a class diagram? And there are a few pointers that hint that it is closer to a domain model. First of all, there are practically no methods here, except the ones I needed for the example. Not that many attributes either, just the obvious ones. The relationships are, well, they are there, but they are somewhat sketchy, some of them. So I would not be able to take this diagram and then know exactly how to build each class. There's too much information missing. So this is probably closer to a domain model. Not that it matters really in real life, because it is you who are using the diagrams, and whether you call it a class diagram or a domain model doesn't really matter. It's how you use it that's is important. So no one is ever going to smack you on the fingers because you call something a class diagram, which isn't a class diagram, and vice versa. I was planning to do a bit of, I'll make a few statements about this diagram, and then I'll explain whether they are true or false and why they are true or false. So let's start with a few easy ones. So in a department, this is, by the way, obviously a university system for some sort. So in a department, I can have any number of students. And this is true because for every object of type department, I can have arbitrary many objects of type student associated to it. That's a good an easy starting point. There are at most 200 courses in this university. Now, this is false, even though it says 200 here. What this says is that for every object of type department, there are at most 200 objects of type course. That doesn't say anything about how many course objects I can have in the system as a whole. If I have more departments, obviously I can have more than 200 courses. Each department can have 200 courses. Any course can only be taught by one single department. This is false, because if I read this relationship in the other direction, I see that for every object of type course, I can have between 1 and 5 objects of type department associated with it, which means that I can co-teach a course between different departments. Right. Student can know other students. And this is true because of this reflexive association. So there's a relationship from student back to student. And it says that for every object of type student, it can have associations to an arbitrary number of other students with the title knows. That arrow, I think, is in the wrong direction, but that's probably because it should be down here and pointing towards the asterisk there. So what can I do as a student if I know another student? What can I do with them? Well, I can use the only methods available, which is bully. So as a student, the only thing I can do is bully other students. Again, an indication that this is more a domain model than it is a class diagram. There are probably other methods available here as well. I haven't gone through the inheritance association, but this is this triangle up here says that a student inherits from person, which means that I can also send emails to them, which is good. I can bully over email. Which means also that every student has a name because they inherit that from the person class. What else? As a teacher, I can bully students. That's false because I have no direct association between teacher and student. The only thing I know about students is that they are persons. I have an association implicit, so as a teacher, I am a person, so I inherit from person, but I also implicitly know that persons then they have names and they have email addresses. So if I get an object of type person, I can email them, and it doesn't really matter if it's a student or a teacher then, so I can send emails to students indirectly then. What else? I can, as a teacher, only be employed by one department. And that's true because if I follow this association here, from teacher to department, there is, for every object of type teacher, there is one and only one object of type department associated with it. I can freelance teach without being employed by a department. That's false for the same reason. This one here says that I have to be associated with a department in order to be a teacher. Any department or anything, or all departments have at least one teacher employed. And that's true because then I'm reading the same association in the other direction, and I see that for every object of type department there is one or more objects of type teacher. If I don't have any teachers employed, I can't be a department. Okay. As a teacher, I can visit lectures, and that's counterintuitive, but if we follow the link between teacher and lecture, we see that there is an association there. I can be involved in any number of lectures, an arbitrary number of lectures, and I've written on the link here that I teach them. So the association description on the association is that I should be teaching the lectures, but there is no way of restricting which methods I can use between classes or between objects in a diagram like this. So as I code this, both conduct and visit will be public methods, and because they are public methods, of course, as a teacher, I could call any of them. If I want to make that restriction, I would probably have to break out into a separate class, and I will say that there is a teacher interface class to a lecture with only the methods that I can do as a teacher, which would be conducting them. And I would have another class which would be a student interface to a lecture, which would then only have the methods that I can as a student do on a lecture, which would be visit. So as it stands now, as a teacher, I can visit a lecture without actually conducting it. And as a student, I can conduct a lecture. I can give a lecture. So I don't have to visit them only. And same thing with the exam. a student can alter exams, I want to clarify with the description of dissociation that the student writes the exams, and this is probably when you start coding, you will interpret it that as that it's writing that's relevant for a student to do. But if I want to have my compiler to support me in this, I would again have to do break out the interface, the student interface to an exam, and saying that the student interface contains writing the exam, and the teacher interface contains authoring the exam. One thing we could discuss, of course, is the write and author method in the right place? Is it the exam that is authoring itself or writing itself, or should those two methods be part of the student and teacher instead? And there would be benefits of that, putting them into the student and teacher classes instead, which would in some sense help with the what methods are allowed to use debate. On the other hand, somewhere I'm going to I will need to fill in the details of a written exam in an object, so the exam object will still have to be there, only it will be added to by the student class, and then we run into other problems when we come to design patterns, that we are connecting those two classes tightly together, so that I need to know the internals of an exam in order to write the exams as a student. And that means that I know probably a bit more about the internals than I ought to. So that's probably a better idea to have the right method down there anyway. But that could be something that we could discuss if we know more about the domain, what the system we're intending to build, and what we have available. We could start looking into the these design patterns, the grass patterns from the course book, for example, how to apply them. As it stands, we don't have enough information to go any further there, but it's open for discussion at least. Right, I think I'll move on. Inheritance, you saw the notation for it, the big triangle pointing towards the parent of the inheritance relationship. We do these in order to classify that there is a relationship of one concept being more specific and the other one being more generic. So it's an is-a relationship. And I can use it for classification purposes only, even if it's not meaningful in the code. Sometimes it will become meaningful. Or I can use it to reuse code, for example, things that are common among all subclasses, I'll put as high up as possible in the inheritance hierarchy so that I can reuse it in all lower levels. Identify what is common between objects so that I don't have to specify that on the lowest level. If we take an example, this is a drawing program, vector-based drawing program, where I have points, lines, arches, polygons, ellipses, and circles. Those are my figures. And just to have a nice deep inheritance hierarchy, I classify them based on how many dimensions each type of figure has. And I gathered all of these into one superclass figure. I have a supertype or a superclass, and I have subtypes. And if I throw in a few methods here as well, I try to put the methods as high up as possible so that they are on as generic a level as possible. So I can draw all figures. All figures have a color and a background color. If I have no dimensions, I don't really add anything to this, but the point will have X and Y coordinates. So I'll put those down there. Maybe I could put them in the zero dimension class as well. If I am a two-dimensional figure, so addition to the color and background color and the draw method, I will have methods for rotating and scaling the figure. I might have a pattern I can fill the innards of the figure with. My rotation orientation will of course be represented somehow in an attribute, and the size is there as well. Different types of figures. The polygon will have an array of points. See little brackets there saying that it's an array. An ellipse will have a center point and it'll have 2 diameters. A circle is a special case of an ellipse with just 1 diameter. And over here, the one-dimensional figures, I have rotate and scale in the same way, and I have a start point and an end point for those two, for all one-dimensional figures. The arch and the line don't add anything to this. They have start and end points, but not much more. The arch probably has a diameter there as well, or a radius. But I was lazy when I did this. I forgot to put that in. What can we say now about this? If I have a pointer to an object of type figure somewhere, that means that I have access to the method draw, and I can read the color and the background color. But I don't know what exactly the type of the object is. If I have a point, for example, it will masquerade just nicely as an object of type figure, which means that my handle can be of figures, and I only have to worry about what type it is when I create the object. So I'll create objects of type point or arches and lines and so on. I'll be creating objects down here, but when I pass them around in the system, I will be passing them around as pointers to objects of type figure. That means that I don't have to worry about the exact details of what type of object I have. I can make do with the most common denominator, or the supertype. If I need to do something specifically with it, if I'm rescaling my figure, I will look for one-dimensional and two-dimensional figures, and I will use the scale method there. I will do two-dimensional figures in one go, and I will do one-dimensional figures in the other go for some reason. If I had put that scale method up in the figure, I could have done with all my figures scale, and of course with the point it wouldn't scale, it would just play along and pretend to scale. That would probably be a better implementation. But as it is now, I have put the methods where they are where the commonality stops, if you will. If I had put it up there, I would have some objects where scale method wouldn't apply. So this is more of a conceptual placing of the methods rather than a practical one. The practical would be to put it at the top, and then I would implement it, have an empty implementation if it didn't apply. Right, I think that probably sums this up. Well, one thing that you might want to be wary of is that, let's say you now want to extend this and you want to say that you have a polygon with curved lines, arches. What do you do then? The problem with these deep inheritance hierarchies is that you may end up into situations where you have to combine different branches of this tree, and that usually leads to problems. So if that is your situation, or you suspect that this will become a problem for you, then there are design patterns, the entity component pattern in particular, that will help you with this, that avoids these deep inheritance hierarchies and instead uses aggregation. I can, of course, just as in my programming language, I can express that I can have abstract base types, which means that I annotated my class diagrams and say that this is an abstract type, and that means that no, I will not be able to create objects of that type. Here it's even more obvious than that if I have a reference to a payment object, it is in fact either a cash, credit, or check object. It just pretends to be a payment object. Right, so diving a bit more deeper into slightly more exotic UML. If I have a relationship, I have, for example, want to model a family, I can do that with, as in the top of this figure, I can have two classes called person, which is actually allowed in UML. I can have more classes with the same name. They are then the same class, and I just repeat them for the sake of putting them closer to where I'm going to use them and so on. It's not something that you see very often, though. But it is permitted. It is permitted to have the same class in several places. So if I want to model a family, I'll say that I'll have a person and I'll have a relationship to other persons, and I'll put a role onto the association. And as with multiplicity, I'm going to read it as I'll start in one direction, in one end, and I'll say that if I am an object of type person, I will, in the role of parent, have an association to one or more objects of type person in the role of child. And if I go the other direction, if I am an object of type person, then in the role of child, I will have an association to two other objects of type person in the role of parent. Now, as I said, putting the same class in two places in the class diagram is usually not that common. What I would do instead is I would make a relationship back to myself. And I'll read that in the same way. If I am an object of type person, in the role of parent, I will have an association to one or more objects of type person in the role of child. And if I am an object of type person in the role of child, I will have an association to two objects of the type person in the role of parent. This is, in fact, if you remember your data structure course, how you would define a tree. You have nodes with one or several child nodes, and in this case it's two root nodes. If you put a 1 there, it's going to be a tree in the classic sense. Right, and here's one thing that you might stumble upon. Sometimes you might need it, but it's rather rare. I don't think I've seen it in the wild, so but for completeness sake, I'll bring it up anyway. So I have company and I have person, and the company employs the persons. Each company employs 0 or more persons, and each person can be employed by 0 or more companies. And that's fine. The problem is that I also want to add a salary. So if I put the salary down here in the person, that would mean that I will have the same salary wherever I work. So if I work as a professor at a university, I will have one salary, and if I also help out, well, say, selling hot dogs in the local football association, I will have the same salary there. That doesn't really make sense. So let's put the salary up in the company instead. And that would mean that the CEO and the janitor will have the same salary, because all employees will have the same salary. Right. One solution is that we will make employment, remember, transaction in some sense, we will make employment a class in its own right. And I will put the salary in there. I think actually I've made a mistake here. There shouldn't be a 0 too many here. It should be a 1 here, I think. And it should be a 1 down here as well, probably. And that side might not be as obvious, but so the way to read that would be that for a company, it will have a number of employments, and an employment is a representation of something between a person and that company then. As a person, I can be associated with many employments, and each employment is associated with one company. That's how you're supposed to read it, if I had done it properly. Now, if I, as a company, want to do other things with my employees, I can copy, of course, everything that's in person. I can copy that into the employment class. And same thing if I want to, as a person, do different things to the company, I would have to copy that interface as well into the employment class, and they would just have a lot of methods that do nothing but pass the method on to either the company or the person. Or I can put a relationship on the side like this. So every meaningful interaction except for the salary goes via this employees relationship instead of through the employment, which is probably close to how you're going to implement it, but it's not the most elegant way to model it in your UML diagram. So what we can do instead is that we can put an association attribute. This brings us back to that we have one relationship between company and persons. And multiplicity is right, that I can be employed by many companies and the company can employ many persons. And that's fine. And then I dangle the employment class as an attribute to the association. It's not associated to either the company or the person. It is a function of the one instance of the association. So one company, one object of the type company, has an association with one object of the type person, and on that one association there is a class or an object of type employment that express the salary. As I say, I haven't seen this very often in the wild. It's an elegant way of modeling it, but I'm not sure how you would implement it. There are a number of different options there, but they all have a few quirks into it. Probably you could get away with some sort of tuple so that you have the company employs, or the company has an associate, or the company has let's say a linked list of tuples where each tuple is a pointer to a person and the salary for that person. That would be one way of expressing it on the company side. Or I would do something which is very close to the previous picture. But the long and short of it is that it's an elegant way of expressing it in UML, but depending on what you're allowed to do in your programming language, you might have to uglify this a bit in order to get it to work. But it's there. If you see it, you'll know how to read it, and sometimes it's a good way of doing it in your UML diagrams. Okay, that was my last slide. To summarize, if I want to, well, we talk about modeling the structure, and this is, I've talked a bit about domain modeling, and I've slid over into class diagrams. The class diagrams, really, there's nothing much more to say about it. We use the same, or rather, when we do the domain model, we reuse much of the class diagram. So when talking about how to do a domain model, I've sort of introduced how to do a class diagram, how to think when you do a class diagram, what is a good class, what is a good placement of a method, and so on. That is something that you need to model the behavior of the system in order to get right. And it's something that you will want to employ grasp patterns and design patterns in order to do well. But just the mere mechanics, this is a class, this is an association, this is what they look like, that's more or less what we've covered today. You will, as I say, do a bit of domain modeling, and then you will do a bit of behavioral modeling, and then you will, as you go on, you will upgrade some of the domain concepts into classes that you intend to build in your system. In that process, you will also probably create new classes and new associations because you need them in order to build a system. But more on that in the next lecture, which is, I think, on Thursday. So I'm stopping the recording now.